Hi, hello everyone. Welcome to this LPS digital presentation. This presentation will cover UV LED measurement principles because this is a very hot topic at the moment due to the pandemic, obviously. And we would like to share some information and some experiences in this field with everyone. My name is Miko Przybyła and I'm the head of Optic, a light measurement quality control company. This presentation was prepared together with Marcin Pelko, who is the head of laboratory at Optic. First, I'd like to present the background why we were presenting this and preparing this digital presentation now for you. Because we've seen a rapid increase in demand for UV measurement services and UV measuring devices, because a lot is going on in the application for disinfection, obviously. We know that UV lamps can help deactivate viruses, including coronavirus. But this is obviously connected with the quality and performance testing of these lamps to be absolutely sure whether they are working well for this application or not. The thing is, of course, that when we are talking about UV LEDs, up until now they were used for still water disinfection and air purification systems in some installations. Because of this higher demand and the development of new LED chips in the UV range, a lot of people involved in R&D and development teams are working on new systems now. They are supposed to replace conventionally used mercury discharge lamps. So now I would like to give you an idea what we will be discussing today. First, of course, we will talk about safety. There has been a lot of discussion going on media and also social media. A lot of products are appearing over there, and the safety issue is really very important. So I decided that we will start with that in our presentation so that we are well informed and we share the information which is approved by bodies like CIE or World Health Organization in this respect. Then we will take a closer look at the available measurement methods, and we will choose the method which is the most applicable for this kind of UV disinfection lamp evaluation. So we will talk about the things related to measuring UV irradiance. I will explain also some basic principles regarding the measurements and the physics behind the UV optical radiation. So the distance and why it's changing everything. Then we will take a look at the angles, so how angles are influencing the performance of UV LED lamps. And we will also take a look at the wavelengths issue. At the end of this presentation, we will also discuss some points regarding thermal stabilization or thermal control during measurements, but the same principles are important in relation to the new systems. Right, so let's start with the safety. We know that UV can kill viruses, and it's killing viruses by destroying their DNA. But it's harmful for all living organisms. So it is also potentially harmful for our skin and eyes. Therefore, you should never use UVC radiation or UVC lamps for skin disinfection. This was also considered by International Commission on Illumination recently. So CIE, together with World Health Organization, has been warning against using UV for disinfection of any of skin area. So bare skin disinfection cannot be made with UV lamps unless it's recommended for medical purposes. There are some standards available. Recently, really 2 weeks ago, CIE issued a position statement on UV radiation, which is able to manage the transmission of COVID-19. And this position statement elaborates more about the measurements, more about the application, the use, and the knowledge we have at the moment regarding UV and its influence on humans, as well as performance in killing viruses. Interesting enough is that a lot of people around the world were actively supporting preparation of this document, and also a national CIE national CIE divisions were actively translating it into different languages. So it's already available in many different national languages. There are also other publications available from the CIE website on UVC risks, and another one on UVC or UV air disinfection applications. These are very interesting documents, including a lot of useful information. So I recommend for everyone who is involved in this subject or looking for some information regarding the use of UV to take a closer look at these documents. They are all free for download from the CIE website. CIE made it open until the end of June 2020. Now, we have to understand that UV is similar to visible light in some sense, but there are some other considerations that we have to observe, and we are supposed to choose the best method. So I'm presenting now something that is obvious for the general lighting purposes, but with this twist towards the UV, which is quite specific. We know from general lighting applications that depending on the subject or the test object, we can make different kind of measurements. Whether it's a validation or conformance to the standard, we can choose different methods. In case of disinfection application, which is the most critical nowadays, we are talking about the measurements in the range between 200 and 280 nanometers, because this is the most effective part of the radiation to kill viruses or inactivating viruses. But important point is that it's the combination of power and time. So it's this dose that we have to provide to be able to kill bacteria or viruses. For this reason, we can use different measurement methods. For instance, total radiant flux, so total emission from this source, can be measured in the integrating sphere. However, when we are talking about UVC measurements, there is a limitation on the size of the spheres available. It's not that we cannot produce such spheres, it's simply because it's difficult to calibrate the whole system. Available reference lamps or calibration sources which are used for total radiant flux and calibration are providing limited signal levels. Therefore, it is at the moment impossible to calibrate larger spheres for total radiant flux measurement in the UV, specifically UVC range. There is also another option to use goniometric system and the calibrated spectroradiometer or a radiometer to check the radiant intensity distribution. This would be critical for anyone who is designing or developing new lamps using UVC sources and want to check the distribution in space, because if we are going to install this in the system using different optics and different shapes and sizes, we have to be sure that the radiation is distributed in a proper way. Since LEDs are very small sources comparing to traditional mercury lamps, for example, the design and the shape and size of the lamp is completely different. And this kind of measurement system can help you to evaluate the distribution. But in fact, the most popular and also the most useful method for disinfection evaluation would be the IRradiance method, because we are in fact checking how much radiation falls on a contaminated surface. So there is a source or an installation or the lamp above a certain surface, and what is important for disinfection process is the dose reaching this specific surface. Therefore, IRradiance method is the most suitable for this evaluation, and it's more repeatable at the same time. The dose that we were mentioning before is going to guarantee the effectiveness of the process. For such measurement, the IRradiance measuring instrument can be used. And this is the example of an IRradiance spectroradiometer with a specially designed IRradiance measurement probe. Continuing with the IRradiance, I'd like to give you some information which is commonly available for everyone in the lighting, but we have to remember that UV is also optical radiation, so all the laws and physics behind this is very similar. However, there are some tiny differences that we have to remember about. Explanation: what is IRradiance? It's an equivalent, it's a radiometric equivalent of illuminance. Of course, in this case, we are not talking about human eye sensitivity, so we are not talking about so-called brightness levels or amount of light, because we are talking about UV. It's an optical radiation. It's invisible for human eye. Therefore, we are using radiometric scaling for this evaluation, so for this measurement. So this is watt per meter square instead of lux. It's only the part of the flux reaching the area. So depending on the distance, depending on the angles, and depending on the optics, the amount of the radiation falling on to the surface may change. And this is something we will be discussing in a moment. The measurement head should be placed flat on the surface, because this is how we are usually supposed to measure IRradiance. So the measurement head is placed in the location where we are trying to measure the amount of optical radiation. And how to perform measurements correctly. This is a very big subject because it is connected with the measurement instruments, with the calibration and the process of measurement itself. What I would like to mention here is that conventionally used discharge lamps are using different technology than LEDs to produce optical radiation in the UV. So the spectral emission is constant because it's a pure physical property of the mercury vapors inside the lamp that is producing the radiation in a very specific wavelength and always in the same wavelength. So for this reasons, for many years, simple radiometers were used and were usually optimized for UVC ranges. And this kind of device can measure irradiance, so can give you information on the amount of energy appearing on the surface. But these meters have their limitations as well. They cannot, for instance, identify different spectral power distributions. So when there would be a shift in the wavelength, such a meter is unable to recognize it. So when you are working on new system or you are performing some research studies, you probably would like to have a full characterization of the source. So it's not only the performance testing, evaluating the irradiance levels, but you would like to have the characteristics of the source in terms of spectral power distribution, dominant wavelength, together with irradiance. In the position statement that was published by the CAE, I can read a section on the measurement. The CAE clearly indicates that the irradiance radiometers can be used for UV measurements, but at the same time, they may suffer from so-called spectral mismatch errors. Because if you are using simple radiometer calibrated for a specific UV range, but your actual source will be slightly different, then the errors may appear, and it's hard to say whether it's a correct measurement or not. Therefore, it is possible to consider using a calibrated UV spectroradiometer for more advanced evaluation. Now I would like to share some information about the dose or the information that are available on coronaviruses. There are some studies, obviously not about on the coronavirus we are suffering from right now, but these are coronaviruses recognized many years ago during different pandemics and during different times. This is something we can use as a reference point. Unfortunately, we will have to wait until the new studies are available on coronavirus, on COVID-19, but this is something we should be taking into consideration. And when you take a closer look, depending on the type or the virus we are dealing with, the dose may differ a lot. So we have to keep this in mind when developing new UV disinfection lamps, that it's the time and the power behind this that is critical. This is available from ResearchGate. This is something you can download. There is an article prepared with this kind of information. So I would say it's something you can use for your application if you are in this field now. Now the distance. Of course, again, it's similar to the general lighting, but I would like to just simply repeat this again, because we sometimes forget about this basic physics. Since this is invisible, we may think there are some other rules, but of course the optical radiation stays the same in the visual and in the UV range. The farther you are from your source, the smaller signal level. You have to remember the dose, because this is critical for disinfection purposes. So when you are designing the lamp or you are making your measurements, you have to remember that the distance is going to change the readings. What about the angles? The same thing. If you change the angle, then the amount of energy appearing on the surface will change. So this graph here shows the cosine correction curve for the IRradiance probe. Because at the zero angle you have full signal level, let's say 100%. When you will be moving this head around, or turning the light source or the UV source, sorry, then you will be observing different readings. This is known as a standard Lambert's cosine law. We just have to keep it in mind. So designing the optics, designing the geometry of the lamp, and then at the measurement stage, you have to remember that you have to position your meter in a proper place. So LEDs are small and flat emitting surfaces. So their primary distribution is Lambertian-like. It's never ideally a Lambertian, but let's say it's a good assumption at the beginning. In reality, LEDs in the UV are usually available with optics installed in front of the LED chip, and then the distribution is already modified. So we are getting more directional distribution. So the radiation can be focused on a specific area, but at the same time we are losing on efficacy, because whatever we put between the lights, the source and the object is going to absorb part of the radiation, and then we are going to lose some of on the efficacy. Now the wavelengths. In the visible part of the radiation, we have many different quantities to check the quality of light. So we can check the rendering properties. We have metrics for human-centric lighting now to help us evaluate whether we deliver proper spectral power distribution or not. In the UVC, it's about pure physics, and it's about the wavelengths. So then again, if you want to kill or deactivate viruses, it's only possible when there is a specific radiation delivered. If there would be a shift in the wavelength, then the effectiveness of the process will suffer. And here again, recommendation on the measurement instrument could be using spectroradiometers, which are well calibrated and which are able to evaluate the system completely. And there is also a specific document from the CA available. It's been published last year on calibration, characterization, and use of array spectroradiometers for measurements of light, and also beyond the visible part of radiation. So I am recommending everyone to use spectroradiometers which are calibrated properly and which are providing traceable traceable data on radiation, because this is critical for this advanced and demanding application. Last thing I want to mention today is thermal consideration. When working with LEDs, we know it from visual range that thermal control and thermal stabilization is critical both for measurement stage and also for performance parameters, because LEDs are suffering a lot from heat, and you have to take it into consideration when designing and also when measuring. So when you are measuring, you can use the guidance on European standard or American standard regarding LED modules, lamps and luminaires, because these standards were prepared primarily for lighting, but also touching the subject of thermal considerations, which is applicable for UV LEDs as well. Again, the wavelength is critical, because conventional mercury lamps are stable in terms of wavelengths. It is unfortunately not the case for LEDs, so you have to check bin to bin and batch to batch discrepancies, because this is connected with the production process and can cause variations in available LED chips. And of course, like for every LED, operating temperature will have a significant impact on optical parameters of the entire system. How to control the temperature? During measurements, we have a standard saying that usually LED chips and modules are measured at 25 degrees C. And how to achieve that? You can use during the measurement thermally stabilized mounts. So they are using Peltier to stabilize temperature at this 25 degree level. There is another method very popular in the production of LEDs, which is a short pulse of 25 milliseconds. And it is assumed that in such a short pulse, there will be no influence on the parameters, on the performance of LEDs, because they will not heat up. At least if everyone is using the same pulse, and then the measurements are comparable. There is also new trend which is helping development teams and system engineers evaluate the LEDs, and this is so-called train method. So there is a sequence of short pulses. Instead of one short pulse at a specific power level, you can use smaller power settings and repeat this pulse at a specific pace. And this is a method which is then allowing you to integrate the readings from the entire period of time and have the possibility to measure LEDs. Also, in this case, avoiding the problem with changing of the temperature of the junction temperature. So what we have learned today, I would like to make a short summary now. First of all, UV disinfection lamps cannot be used for hands or skin disinfection unless it's advised by the doctor. IRradiance method seems to be the most straightforward method to evaluate UV systems, especially for disinfection purposes. Our recommendation then on the use of spectroradiometers is connected with the fact that spectroradiometers can detect different wavelengths and can be calibrated for this kind of measurements. And you have to keep in mind all the physical laws, of course, like distance, angles, etc., because this is optical radiation at the end of the day. It's invisible, but it's very similar to what we can see in the visual range. Thermal stabilization, last but not least, is critical for measurement of LEDs, and then obviously on designing the final LED-based products. And this is all I wanted to present today to you. I hope you found this information interesting. If you have any questions, we will be happy to answer them. And I hope you will all stay safe. Thank you very much. Bye-bye.